title of Towards IoT-enabled multimodal stress monitoring. The contents of this presentation consist of an introduction, background, proposed methodology, experimental result, and conclusion. Internet of Things is taking increasingly a big leap in almost all healthcare processes. One of the most important problems in healthcare is stress. The stress can lead to alterations in central nervous system activity, and its effect can be shown on recorded biological signals such as PPG, GSR, AR, and TR. In our study, we tried to find which signal is the best option for the stress level detection using machine learning procedures. We also investigated the computational complexity in machine learning steps of each biological signals and combination of them to achieve a formation goal. In this part, the recorded signals are illustrated. GSR signals. This signal represents the conductivity of human skin. The mentioned conductivity is directly related to sweating glands activity. PPG signals. The PPG signal uses a light sensor to measure the volume of blood, which is measured by a pulse oximeter on the skin and measuring the amount of light absorbed by the skin. Respiratory signals. These signals consist of abdominal and thoracic respirations. Depth, intensity, and rhythm of these respirations are related to stress level of a person. You can see some example of this signal in this picture. In this picture, we can see the architecture of an IoT-based system for the purpose of stress detection. When the signals are recorded, we need a preprocessing step. In our proposed preprocessing step for PPG and GSR signals, in order to reduce the subject-related differences, we reduce the mean of raw signal of the trained subjects from the train and test signals. For the respiratory signals, we reduce the minimum value of the signal to normalize it. The next step is feature extraction. For the aforementioned signals, many features such as time frequency, and statistical features were extracted. In order to normalize features, the following equation is used. Then the features were reduced using feature score. Those features which had a score of more than half of the highest feature score were kept. Then principal component analysis was done to reduce the dimension of feature into 95% of variance. In classification step, we studied the results of many classifiers such as linear discriminant analysis, LDA, support vector machine, SVM, and convolutional neural networks, CNN, and logistic regression. The dataset which used in this study consists of PPG, GSR, AR, and TR signals of 13 persons with 5 levels of stress were induced, and each trial had a duration of 30 seconds. And we had 70 trials for each person for each stress level. In the performance evaluation for each signal and combination of them, these results are achieved that you can see in this table. As we can see, for the PPG signal, logistic regression outperformed other classifiers. For the GSR signal, bagging had better results compared to other classifiers. Linear SVM was the best classifier for respiratory signals. Multimodal approach, in the case of concatenation of respiratory and GSR, the best classifier was ensemble LDA with bagging approach. For the combination of PPG and GSR, the bagging LDA had better results. And for the concatenation of PPG and respiratory signal, linear SVM showed a better performance. The number of features has also great impact in view of IoT. So we calculated the results with different numbers of features, and results are shown in the table that you can see. We also calculated the number of each signal feature in the combination method, and the results are shown in the circular table. In circular table, we can see respiratory signal have more effect in the classification of stress level compared to two other signals. Each of the classifier has a specific computational complexity. For a two-class linear SVM, we face the computational complexity of D, where D is the number of features, and in RBF SVM, we face D power 2 computational complexity. Because we have 5 classes of stress, and using one against all method, we face computational complexity of 5 multiplied to D power 2 for linear SVM with 5 classes. In ensemble method, we use 10 subset of trained feature for big classifiers. So the computational complexity of 5 class ensemble LDA has 5 multiplied to 10 multiplied to D computational complexity. On the other hand, PCA has F multiplied to C computational complexity, where F is the number of features and C is the number of principal components. As we saw in previous steps, every signal has some information for stress detection, and choosing IoT-based stress detection system parameters will consider many aspects of results and will consider a trade-off between computational complexity, which is based on number of features and the classifier, and accuracy. Thank you for your attention.